Our next speaker is Professor Girish Chowdhury, and he's the director of the field Robotic Engineering and Science Hub at UIUC. And he's going to talk about advances in the digital agriculture and enable prosperous and productive farming for the Kingdom of Saudi Arabia.
Thank you. Thank you for the introduction. So I'm Girish Chowdhury. I'm a professor at the University of Urbana, Champaign. And I'm going to talk about what we have learned about the farms of the future at Illinois and how that could translate to Saudi Arabia. So I'm originally from India, and I did my PhD at Georgia Tech, where Dr. Farhan was one of my professors. And as a memory of those times, I have bought for him gourmet popcorn. When I was a PhD student at Georgia Tech, Eric's lab used to run a number of invited talks, and the agenda would be the speaker would talk and the listeners would get gourmet popcorn. So here's some gourmet popcorn. Okay. So I work on autonomous robots. That's been my area of expertise and interest, primarily in field robotics. And when I started my career working on control systems and adaptive control, this is some of the work that I did at Georgia Tech. Is an airplane that flies with half the wing off, and does useful things. But in the last about 8 years or so, I've been focusing a lot more on agriculture. And primarily because I feel that agriculture is a great area of application for field robotics. And also it's where we need a lot of help right now. I'm also co-founder of a company called Earthsense. And Earthsense is based in Champaign, Illinois, also has an office in India. We are about 30 people with 6 PhDs, and Earthsense is very active in the ag robotics space. And I'm also looking forward to trying to set up some collaborations here in Illinois. I am also the director of the NIFA or USDA Farm of the Future and in Champaign. So this is the single such site in the entire United States. It's selected through a competitive process, and we are really proud that it's in Illinois. What I would like to do today is, again, draw some parallels between what we're thinking about, how the farms of the future should be in the Midwest, and Clay really laid out some of the groundwork for me there, and how we can translate that to the Middle East. I've been to the Middle East now a couple of times. I visited Abu Dhabi, I visited Dubai. This is my first time in the kingdom. But every time I come here, I'm really amazed by the amount of innovation that goes into agriculture, right? So there's of course, water is very important in agriculture in the Middle East. And there's concerns about what happens to the water table when we do agriculture right in the middle of the desert. And then today I learned something about Taif and the rose farms, and I'm beginning to understand more about how agriculture can happen in the Middle East through the use of automation and, of course, water use. One thing that has been really inspiring for me is this Al Baida project. I don't know if anybody's familiar with the Al Baida project. It is a permaculture project. Permaculture is a kind of a opposite of a monoculture, polyculture, in which you have multiple species of plants that help each other. They help regenerate the land. And this is what has happened. They ran this for 10 years, and they started with basically nothing. It was completely dry. And then by the end of 10 years, they started to get some greenness. There's another of such sites in Jordan. So one of these crazy dreams that I have, and it's good to have crazy dreams, I learned that from Eric, is to build robots and digital ag technologies that can reverse the desert. I don't know if it'll be possible in our lifetimes, but hey, it's worth a try. The other things that have been very inspiring for me is just looking at the 2030 vision. I think Saudi Arabia really has the audacity and the vision to think about the future and what can happen here. The coral reef restoration is obviously one of the key things there. So the question I asked myself when I agreed to come here to give this talk is, what are some of those technologies that we need to cause landscape scale transformations, because that's what we're looking at when we think about agriculture in the desert. I do feel that the kingdom is really in a unique position to take leadership in this area, but there are very big technological challenges. How do we scale up? What is that vision for planet scale regeneration? And what do we do about water? And this reminds me of my roots, which are in aerospace engineering. I joined the discipline because I wanted to go to Mars, right? That was my thing. And of course, you go to Mars, you terraform the planet, and you live on Mars, and those are all the science fiction dreams that you have. But more and more, I'm realizing that we need quite a bit of terraforming here on Earth. So let me tell you about that and what we've been doing about terraforming in the Midwest. And my focus is really going to be, at least in the Midwest, a lot on sustainability and regeneration, problems that are apparent with current form of agriculture in the Midwest, and what can we do to reverse some of those problems. So as we all know, we're about to become 10 billion people in not many years from now. And the question is, how do we feed 10 billion people? Really, it's not just about how we feed 10 billion people, but what do we do about the planet? So right now, the environmental cost of producing food is completely out of balance. What do we do to bring that in balance with producing food and produce more food? These problems are extremely apparent in the US Midwest. So US Midwest is the grower of the biggest crop in the world, which is corn. Corn is primarily used as animal feed and for ethanol. Sometimes it's used for food, but primarily it's used for these other things. This is kind of what, yeah, popcorn, that is one use of it, that is food. And of course, high fructose corn syrup, if you know about that one. But this is kind of the corn growing region, about 200 million acres or so. It's a very highly automated form of agriculture. An average farmer or average farmer family has about 2,500 acres of land under control. It's not a contiguous piece of land. It's parcels of about 80 acres spread over sometimes as much as 100 miles. And they grow corn, and corn is nitrogen hungry, which means it just sucks up all the nitrogen from the soil. Corn is water hungry. It takes a lot of water out, and it's large scale monocultures, which have all the problems that Clay was talking about in terms of, you have to spray a lot, and then you have pesticide drift, and you have herbicide resistance, all kinds of things. And we know that agriculture and farmers are not doing really that well, even though Midwestern farmers are probably doing better than many places in the world, like especially from India, from where I come from. Obviously, farmers do much worse over there. But even then, there's more, farming is a risky business. Herbicides are failing, as we heard. There's a lot of erosion, compaction, nutrient loss. And with all of these, yields are behind demand. This is, as you land into Champaign, somewhere around Thanksgiving, this is what you see, right? It's acres and acres and acres of bare land, right? This is what I call the corn and soybean desert of the Midwest. Because in the green season, this is all green with corn and soybean. And once it's harvested, you basically get these acres and acres of bare land. And that's what happens to most of the land, at least in the Midwestern region, right? It's left bare for most of the year. We grow when there is sun, May, June, July, August, September, and then it's left bare. This land could be sequestering carbon. It could be regenerating itself through the use of cover crops and things, but that's not something that's been done today. So here's a video that the company Earthsense put together that I'd like to show. Hopefully we can get the volume.
And right now it's threatened by climate change. To grow people, farmers today have to deal with more frequent and intense droughts, floods, and deteriorating soil. At Earthsense, we've created technologies that'll help farmers produce better food, more resilient soil, and even help reverse climate change. And cover crops are the key to doing that. Cover crops are plants grown not for food, but to capture and store carbon in the soil, making farmland more productive. They're seen as crucial for sustainable agriculture and fighting climate change. They're kind of a big deal.
Farmers planting cover crops so they can reduce the carbon dioxide in the air and get paid for doing it.
Even so, only less than 5% of American farms plant cover crops because of expensive gas-guzzling tractors and skilled labor shortages. Since 2020, Earthsense has worked with farmers to build AI-driven robotics to make cover cropping simpler and more affordable. Terraforming is our low-cost autonomous robot designed for cover cropping and powered by renewable electricity. Now farmers can have fields with robotic fleets that autonomously plant cover crops and, unlike large tractors, do it without damaging the cash crop. With already 30,000 acres signed up by farmers worldwide, Terraforming's advanced AI and low-cost hardware make it easy to start cover cropping all around the world. So let's work together to make agriculture a positive force for the planet by helping farmers put billions of tons of carbon into the ground, make agriculture climate resilient, and heal our planet.
I think the potential for carbon is definitely there, but even without that, just the potential for land regeneration is really worth it for cover crops. So cover crops are a pretty big part of the farm of the future, and doing cover crops with robots is one of the key innovations that we're doing. So how does it work? So the main problem with cover crops is that if you plant them in the Midwest, you have to plant them either with airplanes during the season, which wastes a lot of seed, or you have to plant them after harvest, which is late in September. Because of that, we don't get enough sunlight, and then the cover crops don't really have a good stand. So the key innovation that we're bringing in are these robots that carry about 120 pounds of cover crop seeds, and they can go through the rows of corn and plant cover crop during the season. So these are the robots, and the idea again is that in standing corn, these robots travel through them. 5 of them can cover 80 acres in 5 hours when they're driving at 3 miles an hour. And they distribute the seeds, broadcast the seed. There's really good seed to soil contact because it's so close to the ground. And then around the time of harvest itself, we already have a green stand. So we've been doing these experiments now at the Farm of the Future. This is now the first year at the Farm of the Future of a large experiment, 80-acre experiment. So on 40 acres, we planted with tractors. You can see at the bottom there. And this was done after harvest. And on 40 acres, we planted with the robots. You can see that with the robots, we have a much better stand all the way across the year compared to done with the tractors. So there's a lot of potential in the small robot technology. We've been looking at it today. But I do want to stress one thing. Small is not necessarily weak. So this is a video that we put together of the Terraforming robot with its new brushless DC hub motors to showcase how much power can these small robots pack. So the engineer is loading up the robot. And this is the smallest robot that we have. The one that's planting cover crops is bigger than this. It's called a Terraforming. And then he sits on it. And then the thing pulls a tractor. So I think there's a lot of potential in these technologies. Right, and they will affect us, and they will affect farming in ways that we have not anticipated before. So I'm really looking forward to that future. So looking at that, well, what is possible once we think about swarms of robots that are actually now reliable, sufficiently reliable? We just heard about bathtub curves to go out and do things in the field. And these are just some examples. We can do under-canopy phenotyping, mechanical weeding is a potential. Spot side dressing, cover crop we already talked about, and then of course, you can get into plant manipulation. And this is not new, right? People have been talking about ag and robotics for a long time. We saw a number of papers or number of talks even today, and there's like sessions that run in IROS and IKARA. And this is the question I've been asking my students. Where are the robots, right? I mean, we talk about these robots, we write all these papers, but where are these scaled up systems? And I feel that as a community, roboticists really need to invest more of their time and resources into actually making real working systems and put them out there and make an impact. I mean, the machine learning people have done it. Other areas of computer science and engineering have done it. The time is now there for robotics, and it couldn't be better than today. In terms of cost, I think we've got it down for the hardware. Really, the effect of cost really right now is about the autonomy. And autonomy is a challenging problem in agriculture because of the vast scales, bad data, and just kind of clutter and everything that we have. And as we all know, in farming, cost is king, right? So not only do you have to have very reliable systems, and they have to be more and more automated, but at the same time, the costs have to be brought down. So that has been one of the key focus of the work that we're doing at the Center for Digital Ag and specifically in my group. I'll just highlight a couple of more technical aspects of the things that we're doing now. So we're talking about AI for agriculture, right? So we call it agricultural intelligence. So first, let me start with straightforward kind of perception-based applications. So here what we're seeing, this is a video that Earthsense put together. Here what we're seeing is a robot with a RGBD camera on it. And the robot is going to go through rows of corn, and the AI is going to detect ears of corn, or is detecting the ears of corn and estimating their height. Now this is for high throughput phenotyping. This allows breeders to breed corn with different ear height. And ear height is an important parameter because it drives the effectiveness of the harvesters, and also there's overall a trend towards trying to breed shorter corn, which are more water efficient. So this is with an NSF project called Crops. What you're seeing here is a field map. In each of these grids, a different variety of corn is planted, and the robots can go through there, measure the heights of corn, and then report that as data. And those measurements seem to match really well with what humans are measuring. Now here's another video of the same technology, which is not yet prime time, but you guys get to see it. Here, not only is the robot detecting the ears of corn, but they're tracking them. And you can see this is like, now the technology is basically at a point where I will say we're at with medical imaging, where humans are not going to be able to do this. Robots, the AI, is much better at finding those ears of corn and estimating their height than humans in terms of accuracy and in terms of speed at the same time. So it's very exciting where we are today with the kind of AI technologies that we can bring to bear in these types of problems. And I think the same thing can be used in the coral reef problems too, right? Once you have these types of cameras and AI on the underwater robots, they can also detect and track objects of interest. That's one. The second is autonomy, which is, of course, my wheelhouse, and a lot of my students work on this. So I'll first start talking about work that Erkan Kaykan did. I think some of you know Erkan. I think at least Yingxi knows Erkan. He was from Daniel Russ's lab. So he worked on adaptive moderative control in the sense that these robots, when they drive, they slip a lot. So you have to estimate their traction parameters. So in this model, they're denoted by mu, mu, and kappa. And then I'm not going to go very much into the technical details. If anybody wants to sit down with me and go through that, I'm available today and tomorrow. But basically, Erkan put together a nonlinear moderative controller and a nonlinear moving horizon estimator to estimate these parameters. And then we implemented it, and it worked really great. And this led to a Best Paper Award in 2018. But the problem is, and this is, I would say, kind of the state of the art in agriculture autonomy, right? You use GNSS or GPS with some inertial sensors to basically go down the roads, the survey grade GPS kind of thing. But the problem is, once you go under the crop canopy, that GPS signal becomes not as reliable because of multipath. So instead of getting 2 centimeter accuracy, you're now getting about 40 centimeter accuracy because of, again, the signals bouncing off. So you can't just use GNSS once you're under the canopy. So here we started then in about 2018, starting to formulate this problem of row-based navigation, right? So we tried to use, SLAM and all the kinds of standard techniques that one could use with robotics, and found that it's very difficult to bring those techniques to agriculture. If you know a little bit about SLAM, there's a lot of aliasing going on in a field because all the corn looks exactly the same as all the other corn that's out there. So we created we had this idea that we just get to the point, right? So estimate the distance to the row and the angle with respect to the row from the perception data. And we've published a couple of papers that did this with LiDAR. And this video kind of shows what that problem is. So this is the point cloud. So here is the LiDAR. The robot is driving up the row. And this is what the robot is seeing in terms of the range measurements. And what the AI algorithm has to do is fit lines to this. Right? So it's very, very challenging. There's a lot of outliers. It's very non-Gaussian. So we came up with, several techniques. In the first paper, we have basically a very fast ransack implementation that is guaranteed to converge and results in fairly good performance with this. And of course, the key, again, that's what I've been saying. is we really need to get this technology out of the lab. So it's not enough to just, do a test about for 20 meters and then write your paper and then move on. We like to bring it out there. So we have implemented this now on more than 100 robots, and then we're not nice to the robots because, they're field robots. They need to be out there and be roughed at it. So this is me. This is, I think, 2020 or something, trying to give this robot a hard time, and it's doing pretty well. So I think that's important, right? How do we create reliable systems? And we've been, working on it. In 2023 IKARA, we will have another paper. This is now a system that's at a higher level. It basically determines whether the robot is inside a row, outside of a row, or crashed. And based on this high level supervisor, then it switches between different policies, and then each of those policies can be added. So there's a lot of modularity here. There's learning, but that learning is at module level, not end-to-end learning, because we want to have a system that is debuggable and solvable. So here's a video of that. And if you go to IKARA this year, then you will see this. Let's see if this video always gives me trouble. Doesn't like, I don't know what's wrong with that video. Anyway, the robot works. We'll move on. We'll see something else. So the problem with GPS, the LiDAR though, is that LiDAR in itself is not enough for under canopy navigation. That's because with the LiDAR, all you're getting is these range points, right? You're not getting any semantic information. And also LiDARs are expensive. The cheapest LiDAR that you can get that's good enough is about $1,500. But we want to have the whole robot cost less than $500. So how do you do that? One way to do that is with visual navigation. And visual navigation in agriculture has a lot of potential, but it's extremely challenging because of all this craziness that you basically see in an agricultural field. So we came up with a system called Crop Follow, which was published in RSS 2021. And what that does is that it basically takes in an image, a monocular image, and then outputs distance to row and heading to row, similar to what a LiDAR would do. And it's trained with a lot of labeled data. And again, I'm not going to go through the details of this. It probably can be done at a different point. But that's the output of the system, the perception module, that then feeds into your standard robotics modules like a extended Kalman filter, into an MPC, and then that generates a path. So this is a pretty reliable system. Let me show you some videos of it working in different stages of season. So it's the same robot with the same monocular camera, and it's driving autonomously across these different stages of corn. And then now, instead of me kicking the robot, I have my student kick the robot. And now you'll notice that the corn, this is soybean actually, and it's quite small. So it's certainly not using the LiDAR, it's using the vision to navigate. Also, unlike in 2021, now the 2022 robot has speed control. So it's able to brake and then get back on track. So these robots are starting to get quite reliable. And we continue to improve that autonomy and get it to do better. And then I think at this point it transitions into corn, or at some other point. Where's my mouse? Okay, this is. Oh, you know what? That's why, because I'm using the wrong computer. So yeah, then it seamlessly transitions into corn, and then it continues to go. Yeah, so now if we have time, we'll see the other video too. Anyway, the other things that we're doing is going beyond waypoint-based navigation or going beyond GNSS completely. So here, I mean, obviously, you're in the row, you're following the row. The broader problem is being able to find paths when you see obstacles in front of you. Now, obstacles can be of two types, right? A geometric obstacle in the sense that it's physically there, like this plant, it's right there, or a obstacle that's geometric but traversable. For example, if I have grass to a LiDAR, geometrically, it looks like it's an obstacle, but I know from experience that I can go through grass, right? So there is this semantic aspect of it that also needs to be learned and developed. So yeah, So we have this system called Wayfast that we publish in IROS. And the idea is that you get an RGBD image and it outputs a predicted traction map. And then based on this, then now that feeds into the MPC and it drives. So I'll just skip to the interesting part, which are the results. So here's basically this system. Now this is all learned in a fully self-supervised way. The robot has learned to figure out what's a traversable and what's not a traversable obstacle. So you'll see that it avoided that ditch a little bit. It can go through grass. It's learned that it can go through grass, but it avoids trees. Similarly, it knows that snow is not good because it loses traction in snow, even though geometrically snow looks just fine, right? It looks like hard ground. So we're quite excited about this technique. I mean, these are just some videos, I think, just a more close up of the same things. So this was a test we did in December in snow, and we're beating most of the other methods that are out there right now. And of course, we get to go to exotic locations to test these robots. So we enjoy that. This is in Puerto Rico. So then coming back to the opportunities in the desert, right? So one of the things that I'm quite inspired about is the Oasis agriculture, right? So in Oasis, you have limited land, limited water. So what do? The wisdom of in the Arabic countries has been to do polycultures, right? To have systems that build on top of each other, and these are again there's a lot of evidence that it can be done. So Jeff Lawton is one of the key people who's been doing this. He's done this in Jordan. He's also done the Al-Baida. I think Jeff Lawton was the key person behind it. So the question is, how do you scale that up? And one of the aspects of that is automating some of the manipulation tasks. So one thing we're doing here, and I'll skip this quickly, is creating these robots that are inspired by octopus arms and elephant trunks, soft robots that cost very little because they're essentially 3D printed with different windings, and you pressurize them and they bend in different ways. And then, putting them on small mobile robots to go out there and do things. So the idea is that, if the berries are outside, then you can just grab them. But if the berries are inside, then you can extend these arms and reach out and then and do manipulation. So there's a lot of very interesting manipulation problems here that are being tackled, and I'll kind of skip this, but we some visual navigation problems for the arm, similar to visual servoing. Finally, I just had to put this plug in because we have looked a little bit. I'm not at all an expert in underwater navigation, but working with Andy Singer, I've been looking into acoustic localization. I'm an expert in localization, so we've been looking into acoustic localization of underwater vehicles, and there's pretty interesting results that we've gotten. We had a paper last year in RAL and also in IROS, I think, where we were able to basically show pretty good performance with underwater localization using time of flight and Doppler estimates to get the accuracy. Okay, so I think that brings me to the part where we continue the conversation after my talk, which is how do we design and deploy new technologies for the opportunities in the desert. Of course, water harvestation, water retention, soil regeneration. I think there's a lot of potential in cover crops in doing that. We have to find out how exactly it can be done in the desert, but that could be done. Coastal area restoration. And this is a new idea that has been very interesting, like, robotic oasis gardens to supplement the tourism vision that the kingdom has. Would be pretty interesting to be in a resort where robots are looking after the roses and tourists are having a great time looking at that. It would be great for the kids. And of course, the ultimate goal is land regeneration and reverse desertification. So that's it. And I'm here today. I'm here on Thursday all morning. And if people want to catch up with me, I'll be around.
Yeah. Thanks, Professor Girish, for your wonderful talk.